Alright, we're back. This is part 7, and we'll move on to Heisenberg's uncertainty principle. Alright, this principle is proposed in 1927, suggesting that the wave nature of matter imposes a limit to the precision to which we can measure both the position and momentum of a particle simultaneously. Alright, so quantum theory predicts that it's fundamentally impossible to make simultaneous measurements of particles' position and momentum with infinite accuracy. Therefore, there is an uncertainty in the momentum and the position of a particle which arises from the quantum structure of matter and not due to imperfections in practical measuring instruments or techniques. Right? What this means is that the uncertainty we talk about here in Heisenberg's uncertainty principle, right, is not a measuring tool problem or human reaction time problem as we have learned in chapter 1. So in chapter 1, the uncertainty we deal with is something to do with the fact that if we look at a ruler, right, this is the smallest division of a ruler, right? So this smallest division is what? Let's say it's 0.1 cm, right? The smallest division, the smallest gap in the ruler is 0.1 cm. So if I measure something like that, but this something doesn't touch either this or this, I have to sort of estimate, right? This is the estimation and this can be an uncertainty, right? This problem can be solved by using a more precise instrument. That means the gap is smaller. So that means if instead of 0.1 cm I use vernier caliper, there's 10 more gaps, right? So isn't it the uncertainty improved? Because now I can read this object to this point, but there's a marking here, right? Or at least a closer marking here. So the uncertainty becomes smaller, right? So this is what we call imperfection in practical measuring instruments, right? But Heisenberg uncertainty principle is not referring to this type of problem. Okay, it's a different type of uncertainty and it is a feature of quantum theory. That means it will happen, it cannot be eliminated, right? So this thing can be, if not eliminated, at least improve a lot. I can reduce uncertainty a lot, right? But Heisenberg's uncertainty principle, this uncertainty is a feature of quantum theory. Okay, so it cannot be removed and it's nothing to do with practical measuring instrument issues. Right, so I'll try and explain one perspective of Heisenberg's uncertainty principle here, right? Hopefully you understand this part, right? So from de Broglie equation, we've looked at this a lot, so don't go talk about this, right? If I know the momentum of a particle, right, precisely, then the wavelength is also known precisely because if, let's say I know electrons mass and velocity precisely, so P is one number only, there's no uncertainty. Then therefore lambda is also known very well because if one value of p means one value of lambda, all right. So if for me to have a wave function, right, that represents one lambda, right, that wave function needs to be completely unlocalized. What does completely localized? Okay, it needs to be a sine function or cosine function, and it needs to be unlocalized. What does unlocalized mean? Unlocalized means that the wave stretch to infinity. Right, that means this wavelength, okay, I'm not drawing very well, but I'm trying to exemplify the point that this wavelength lambda must be consistent throughout the wave, right? Then this is the only way I can get a very precise momentum, is if my lambda or wavelength is very precise as well, right? But if you have very precise momentum, because you have very precise lambda, the lambda requires your wave function to stretch to infinity. That means to say that your particle can be anywhere in this length. So your delta x, your uncertainty in the position of the particle, become the whole length of the wave function. Okay, so hopefully you follow that. So that means this, in this case, delta p is very small. Almost zero lah. We can say it's almost zero. Well, theoretically cannot hit zero lah, okay? But the delta x will be very large. You see that? This is nothing to do with measurement instruments. Okay, then let's look at the other case. Let's say if I know the position of particle more precisely, that means that as per what we learned earlier, right, the part on this thing, right, you can see that if the wave function only got like that and like that, then it doesn't stretch anymore to infinity, then the I know the uncertainty in the position to be here. Correct? This is delta x, right? That's uncertainty position. The particle has to be somewhere inside here or somewhere inside here. this is not a possibility and this is not a possibility. All right. However, in reality, the wave function don't look like that. Okay, this is never mind. Don't worry about it. There is such a wave function, but this is not wave function of that a particular electron, for example. All right. So don't worry too much about this. All right. We'll just try and take the point that in this type of system, right, the particle has to be found somewhere here, and not here, and not here. Right. So the delta x is here. Okay. However, if we talk about a generalized idea of a particle, right, to be able to get smaller delta x, because this infinite delta x, right, this delta x is infinity. From here to here is infinity, right? To shrink it, delta x to this value, right, what I have to do, right, is I have to sum many pure sinusoidal waves like that. So what happens when I sum many pure sinusoidal waves like that is I superpose them like I superpose waves, right? So I'll try to show you how do I get this. So it's something like the wave like that, right? Then superpose with a wave like that, right? Another wavelength like that. Then so on and so forth. I keep superposing more and more of these things on top of this thing like that. Then I sum the amplitude. So you can see that probably this plus this sum to some high value, but later on I can draw another waveform like that and maybe like that, such that the sum of these four actually sum to 0. Right? So as you sum more and more waveforms like that, like 1, these are all pure sinusoidal waves, 3, 4, 5, right? What will happen is that you will sort of destructively interfere in this region and in this region. And then only in this region, you have some form of waveform. So only this part will retain some form of waveform, and the rest here and here sort of totally kill each other. Because as you draw a line down like that, you will see that this one is positive, this one is somewhat negative, right? This one is a bit negative, this one is a bit positive, this one is a bit positive. But if I add some more and some more and some more, you realize that they'll sort of sum to 0. Right? So that's why the left-hand side and right-hand side of this wave, right? This wave here and this wave here start to disappear as I sum more and more sinusoidal waves. Right? So when this thing is a superposition of many pure sinusoidal waves like that, right? The delta x become smaller, but my delta p become bigger. Why? Because now my delta p, you see this delta p, this delta p here of this one wavelength wave function, right? There's only one value, p. But if you look at this one, how many momentums does it have? Each of these pure sinusoidal wave is a different momentum because p equal h over lambda. Alright, so this one got different p, 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 this one got different p. Each of the p can be calculated by h divided by lambda, where this lambda is substituted here to find this p, and so on and so forth. So each one of these waves that I sum to get this one, to get smaller delta x, will contribute to a different p, which means my delta p is getting higher and higher. So if I add more wavelength, this x drop, but delta p get higher. Okay, so this is the idea behind why this is a feature. That means to say, this is just how quantum things work. It's nothing to do with measuring device. Okay, so that's the idea. Okay, so again, this perspective, right? If you understand very good, don't understand, I think it's okay. Not super important, in my opinion. Okay, all right. So, but this part you must understand, right? If the measurement of position is made of uncertainty delta x, and a simultaneous measurement of its x component momentum is made with uncertainty delta p of x, right? So the uncertainty momentum here is talking about the x direction momentum. The product of the two uncertainties can never be smaller than h, where h is Planck's constant. Right? Is there a gap here? Sorry about the gap. No, never mind. Right, I'm not sure why it's just Planck's constant. This principle implies that it's possible to simultaneously determine both the exact position and exact momentum of the particle. The more precisely one quantity is measured, the less precisely the other can be known. Heisenberg emphasized that these uncertainties are a fundamental aspect of quantum mechanics, arising from the wave-like nature of matter at the quantum scale, rather than from any limitations in the measuring instruments, right? Which is what I tried to explain to you earlier. Where Heisenberg uncertainty lead to the following consequences: you cannot simultaneously be precise about the position of the particle and its momentum. You're not able to predict precisely where the particle will be in the future, right? So we are not able to state the position of subatomic particle precisely. We can only state the probability of where it's likely to be. All right. Hopefully, you understand how Heisenberg uncertainty principle actually ties in with the idea of wave function and the probabilistic nature of where the electron is. From this statement, right? We cannot state the position of a subatomic particle precisely. Subatomic particle refers to the electron. We can only state the probability of where it's likely to be. So I refer back to the example where I talk about the two-hand experiment. Let's assume that the electron is in this two hand or within this part or this part. The electron doesn't exist in either hand if I never go and check where the electron is. It's a probability distribution function. So it doesn't, it neither exists in the right or the left hand. It's a 50-50 probability, right? Until I check, right? If I check, it's called a measurement, or people call it observation or measurement. But I think the more accurate term in the scientific community, they like to say is a measurement, right? So if a measurement means that I go and somehow check whether the electron is in the left hand side, which is between OQ, or between inside the right hand side, which is RQ, right? Once I check, the electron becomes a particle. A particle no longer means that it's either that means it's 100% here or 0% here or vice versa, right? I can also check, open this hand and find that it's not here. So if I open this hand and find that it's not here, that means I know 100% is inside here. Okay, can you understand that, right? So this is this a bit similar to the idea behind the Schrodinger's cat, actually. Yeah, but I'm not going to touch that since it's not in syllabus. Okay, yeah, where were we? Right, so yes, I want to go through the video. So I'll try to give you an example of how this actually happens in light. All right, so here we're talking about actually single slit, not double slit, sorry. This, I think, single slit experiment. Okay, never mind, watch the video. Right, so this is the single slit experiment. You can Google it yourself. Okay, I'm sorry I didn't center this. Let me try to center this better. All right, let's go. Right.
Today, I'm doing an experiment that demonstrates Heisenberg's uncertainty principle. So here I have a green laser, and I'm firing it down towards the front of the room through a narrow slit. Now that slit can be adjusted, so it can be made narrower or wider. And the laser spot is projected onto a screen behind it. So what do you think is going to happen to this spot on the screen as I narrow the slit? Well, let's have a look. You see exactly what you'd expect. The spot gets narrower and narrower, the sides are getting cut off.
So this can be explained very simply. As the slot gets narrower and narrower, right? I mean, less and less light go through. So you should expect that these two dark positions actually close in on the light.
By the slit makes complete sense. And if you stop there, you would never realize that Heisenberg's uncertainty principle is at work.
Okay, at this point, Heisenberg still not physically manifested, but it's going to be shown.
But if you keep going, something strange happens. As you make the slit even narrower, the spot...
Okay, note that if you look at this part, right, you can see that this part, he's closing the slit this way. That means delta x is this way. Delta x is horizontal. Understand or not? That means to say that it looks something like that. Delta x looks something like that. Right, so delta x is horizontal, which means that as I make the slit closer and closer, delta x getting smaller and smaller. That means I'm more certain about where the photon, because this case is light, is laser, so where the photon go through the slit, I'm more certain. So delta x gets smaller, which means delta p must get bigger. So if delta p get bigger, I'm more uncertain about how the electron move in this direction, because delta x is this gap, so delta p is uncertainty in the motion in the same axis, which is this side. So that means it may go more left or more right. So you will see the effect now.
The spot starts to spread out.
Can you see that?
Isn't that incredible? You're making the slit narrower, and yet the spot on the wall is getting...
Yeah, why is it? The slit getting narrower means delta x is getting smaller. Then, because I'm hitting Heisenberg's uncertainty principle, we say that delta x and delta p must be multiplied together to get greater than h, right? So if delta x becomes smaller and it becomes too small, delta p is forced to increase because it must fulfill the criterion that delta x times delta x times delta b greater than h, right? So that's why it starts to spread out like that. Okay?
It's getting wider. The narrower you make it, the wider that spot on the wall becomes. To understand this, we have to look at Heisenberg's uncertainty principle. Heisenberg's uncertainty principle is normally written as delta x delta p is greater than or equal to h on 4 pi. So what does this mean? Well,
here I'll just note that this is the more accurate version, but in your syllabus, we don't care about the 4 pi. right? So we use a less accurate version. We just delta x delta p is greater than or equal to h.
About the position and the momentum of a particle. So x is the position of the particle and p is its momentum. So delta x is the uncertainty in position and delta p is the uncertainty in the momentum. Now if you multiply those two quantities together, they must always be greater than or equal to h on 4 pi. Now h is Planck's constant, and that deserves a video all to itself, like this one by 60 symbols. But for our purposes, it's just a very small number. So in our everyday lives, we don't come up against this uncertainty relation because everything is much, much bigger than h. But as we narrowed the slit, we were decreasing delta x for those photons. So we were getting more and more precise about where the photons were passing through that slit. And at a certain point, you come to this limit. So that if you narrow this any further, you're going to break this uncertainty relationship. So what needs to happen is the uncertainty in momentum needs to go up. I should specify this is uncertainty in momentum in the x direction, in the horizontal direction. So if before photons were going perfectly straight, now they must veer off to the left or to the right to ensure that we don't break Heisenberg's uncertainty relation. And the more you decrease your uncertainty in position, the more narrow you make that slit, the more the uncertainty in momentum has to go up. And so if these photons are going to the left and the right, that's going to produce a much wider beam. It's really, really non-intuitive, but it's the way the world works.
It must be the sun playing tricks with my mind.
Yeah, so that's an excellent video on Heisenberg's uncertainty principle. And we're getting close to the 20-minute mark, so I think I will stop before I go on to electrons. All right, see you in the next lesson.